Maybe should we wait a bit more, or do you think that's like everyone who wanted to come?
I think you could start.
Okay, awesome. So thank you everyone for coming. I did not expect that many people to come, so this is great. So we're gonna talk about like the fundamentals of machine learning, like I said in the uh, like description of this presentation and session. And at the end, I'm gonna give you some workbooks you can follow for you to learn how to code your own machine learning models in PyTorch, which is a library for Python. So yeah, let's get started with that. So the bit about me, I'm a high school student from Wolfsburg in Germany. I'm 17 years old, and I was previously an intern at the German Aerospace Center this year. And my primary interest is in computer vision and machine learning. So that's why I'm showing you like how the fundamentals of this works today. The core concept of every machine learning task or AI task is you have an input in numerical data. So some kind of numbers in every format. You could have like literal numbers, or you have images, and then you have pixel values for each pixel, right? The RGB values or the hex values, and those are your numerical inputs. Then you perform some kind of mathematical operation with them, some functions, and they have a learnable parameter. We call them these parameters theta. So this symbol here, this Greek symbol, this is like the parameters of the model you have, and they get modified and converge to a point where it models the output prediction the best. So the most simple task you could have for a machine learning model would be linear regression, like this, where you have like a function and you try to converge with, like you to perform linear regression so it fits the points with your data points best with the least amount of loss. So the loss is kind of the error you have in your prediction. That is how wrong it is, essentially. And the aim of this function is to decrease the error of the prediction, to decrease the loss, and you do that by modifying the parameters in a certain way. So the formula of this would be that your prediction, y, would be the weights. So W is the weight times X is the input number, plus a bias, that's B. And in some cases, not in every case, you wrap everything in an activation function, F, and that can be everything. Common ones are sigmoid for like if you want more distributed things, or ReLU for nonlinear models. So essentially, it could look like this. If you have multiple input data points, you use x1 and x2, multiply that by a weight, add a bias, and then you get your output prediction. This is one layer though, and you train your model, like you train your weights and biases in this process. So you perform forward pass, you initialize your weights randomly, you have a random value, like v is 0 and v2 is, for example, 1, and the bias is 2, for example. And then you look if y is close to the prediction or far away from the prediction. If it is far away, you modify with those values to get closer. And you do this first, you zero the gradient. So before you calculate the loss, you also have like other gradients you had. So you zero them to sort of reset the training process again. Then you perform backpropagation to know which of these parameters, is it W1, W2, or B, that is the most responsible for the inaccuracy of this prediction. And once you calculated which one is responsible, you perform gradient descent to know in which direction to modify these values, so the prediction is more accurate. And gradient descent, you can think of this like this loss landscape you can see in this image here, right? So you have this loss landscape, this is the loss, and the aim is to decrease the loss to the minimum point that's possible. So which would be in like some here, and you start at a random point with random values, and then you try to decrease the loss. So when you start here at the top, you modify the parameters for the loss to go down. And normally you start with big steps. The steps you take, this is called your learning rate. If you see this in like some machine learning things, but So you start with big steps, and then they get smaller and smaller the closer you get to the conversion point. So for classification tasks, like this works for linear regression, right? Like this. But for classification tasks, you obviously don't want to like model a number to another number. You want to know which of the categories is like the classified. So to do that, you have not one output, not one y, but multiple ones. So y1, y2, y3, and these are the number of classes. For example, here I have like a simple table, an example with 3 classes for cat, dog, and fish. And so if you see this cat image, obviously that's a cat. And in this case, the model is already quite accurate to determine which of these classes that image belongs to. So the output of y are raw logits. They are not normalized, they're just like some number. And then you transform these logits into prediction probabilities with a sigmoid function, so they all add up to 1. And then if you have binary classification, so 2 classes, either A or B, then you just round the values and take the one with the higher one. Or if you have multiple classes, you just take the maximum value. And in this case, this would be 0.83, which would be label 1. So cat is the class this image belongs to. If I'm too fast, feel free to ask questions in the end. We can go over every part more slowly. So this is just one layer that I showed, but in most tasks, in most problems, you use multiple layers that are next to each other. So in this case, you can just use, this is only for a very simple task with linear regression, for example. But if you have more complex tasks, like, for example, determining which class an image belongs to, you need more complex categories to model this, which is why you combine multiple of these different calculations, multiple of these layers into a neural network. So the neural network is like modeled after our human brain, how the neurons work, and they have like each neuron is connected to another neuron. In this case, we have 4 layers, 1 input layer, 2 hidden layers, and 1 output layer. And these hidden layers are like just calculations you do. The input layers are your input data. So for example, this could be every single pixel value from an image. And then you perform calculations with them, multiply them by a weight, add a bias to get this neuron, but do the same for this one. And in the end, you have like one number, one output to say, okay, is this a cat or is this image not a cat? For example. So the formula for this would look like this. You have your prediction. That prediction for the next neuron is the sum of all the neurons, all the values of the neurons before, and their input multiplied by the weight, and then you add a bias afterwards. I left out the activation function here because it's like a bit too complex, but like normally you can also add an activation function if you want nonlinear relations or other things. But like this is essentially the core formula of a neural network. This is how it would work. And then you modify the weight and bias with the steps I told you, like here. Forward pass, calculate the loss, zero the gradient, so reset the training process. Perform backpropagation to know which neuron, which parameter caused the error, and then modify that parameter so the prediction is more accurate. This is the core part. And there are multiple types of neural networks. This is the most simple one. This is called a feed-forward neural network, or just normal artificial neural network. So this is the core idea behind it, but there are multiple variations of it. So the one I want to talk about the most today is convolutional neural networks, because they are the most common type for computer vision tasks. So for classifying images to know, or for example, for detecting pedestrians for an autonomous car. So these have a lot of practical implementations. I know a lot of you are interested in medicine. So convolutional neural networks would also be the ones that would, for example, determine whether an image is a tumor or not. Like they are the AI models that could detect cancer, for example. So these work a bit different to the normal neural networks. So they have this feed-forward neural network, but only in the end part. Before they have convolutional layers and pooling layers. and they are specifically designed to process images better. So you start off with convolutional layers, which are essentially filters. You have a kernel here, and you calculate each of these values. So this is essentially the feature map. This blue thing is like the original image, which you have, for example, grayscaled, and now you have like values from 0 to 1, normalized ones, whether this is like a black or a white pixel, right? And then you have like your image here, and now you want to determine whether there's a tumor or, for example, whether in this image is a cat. Then you have this kernel here, this is called a kernel, and that kernel performs mathematical operations on this feature map, this image, essentially, and this is like a filter on Instagram when you, for example, grayscale it or make it brighter, right? But the numbers, the parameters with which the filter is operated, they are learnable just like the weights and biases. So you update them, and this also helps with the prediction. So in the end, you have lots of feature maps, and some of them are for more complex features, others are for simple ones. So, for example, of a cat, one feature could be to detect an ear, right? And the more you get, the deeper you get into the neural network, the deeper the features get. After the convolutional layer, you have pooling layers, and essentially that's just to simplify the computation process, because you need lots of calculations for this, lots of computing power. So most of the time you don't want to spend that much money on compute. That's why you simplify this by taking the maximum value, for example, in max pooling here. Another common thing is average pooling, where you take the average value of a certain block of this feature map and sort of condense it, compress it, so it's easier to calculate. Because when you have multiple tens of thousands of feature maps, in the end, you need to flatten them out and then input them into your normal neural network, your feed-forward neural network that I showed earlier. So if you have millions of input numbers, it's also not only hard to compute everything, but you need lots of data to train your parameters efficiently, because you have tons of parameters you need to train. So that's why pooling layer is very important. And you loop through them a bunch of times, convolutional layer followed by a pooling layer, multiple different times. In the end, you flatten all of your feature maps out. So you have these maps, like here, for example, this feature map, and each of the pixel values gets flattened out. So you have one value, and they are inputted in your normal neural network as input data and calculated normally as we did before. There are also other types of neural networks, which I don't want to cover that much, but if you're interested, we can talk about them more. So one is recurrent neural networks. They are very useful for temporal data, because they map time essentially. And then transformer models that are the core part behind LLMs. So natural language processing and ChatGPT and Gemini, those are all based on transformer models. They have a special thing in them before your normal neural network that's called self-attention. And you have multiple self-attention layers to calculate and perform operations with language better. And then diffusion models, which are useful for generating images. They start off with like a image of noise, and then like sort of condense that noise into a image or some other data. Could also be audio, for example. And generative adversarial networks that are these things are also for generating data, like generating images, generating audio, and they consist of two parts: a generator and a discriminator. The generator generates the image. The discriminator tries to distinguish, is this image real or is this generated? And this is sort of, they compete with each other and get better over time. So in the end, you end up with nice images, for example, in this case, or video. Okay, so we could cover, I know this would be optional, so you guys get to choose which one we can cover, but I have notebooks here in Google Colab, which I found and I wrote, and I think they are really nice at explaining the parts we covered in theory now and like implementing them in practice. So we have the fundamentals of tensors. Tensors are like the numerical type of data you need to process, right? You use tensors for processing. Essentially, those are vectors. Then it can cover, we have a linear regression model we could go over to program a classification task. So like your normal classification, but not for images in this case, just for numerical data and CNN and computer vision. But this is a bit more advanced, so I would rather go over this one. So if you have any preferences, which we could go over, or if you have any questions first, you can ask them now, so there are not any unclarities. Feel free to just raise your hand or unmute yourself.
Right. If anyone has any questions, please leave them in the chat box. If not, we can conclude the session.
Okay. It was just 15 minutes. We could go over a notebook I wrote. Like that would be the code. Okay. How can you show the minimum model? Yes, that's a very, very good question. So this is a very common problem you have. It's called overfitting. When your model gets too, like it is too reliant on the training data, and it's not general enough, right? It can only model the training representation of data. And if something new happens, which it has not seen yet, that's irritated. So there are a couple of things we can do for this. One thing is if your models are far too large, so billions of parameters, they tend to overfit easier. So if you make your models smaller, they focus on more of a fundamental like categories which you need to model your output prediction. So that's one thing. Another thing is dropout. So in training, when you perform all these steps, you eliminate some neurons in the calculation process, and that ensures that you don't rely on them too much. So for example, when you predict an output, you just say, okay, 50% of the neurons are used. I just don't use them in this training process and see if my model is still accurate in classifying this correctly. So those are some ways, but this is a very common problem. There are a lot of ways to deal with that. Okay, another question for pooling. We have dimension. Yes, you have to ensure you don't pool them that much. Like if you have an image and you pool them into one pixel, of course you can't classify them that much. But this also ensures you don't rely on that like specific features. So if one pixel is right next to another, that's not like it's not that important, but you focus on more the fundamental parts of an image. So you can think of a pooling process as sort of making the resolution of the image less and less like so the image gets more blurry in that case. But yeah, that normally that you have to make sure that you don't do it that much. But yes. But you most like about machine learning. I think it's very fun if your model converges. So if you have your loss function, it just goes down. That's the most fun process. But I like computer vision the most. That's the most fun task for me. Where's for more than one variable if it's one picture of a cat? Okay, so the variables you have, the input representations is not the image. Okay, you get your image, and if you don't use a convolutional network, you get each pixel of that image, and each pixel of this image is like an input data, right? So when you have like a pixel that's like white, 155, you normally normalize them. So you have one, and each pixel of image you flatten them out. These are your input. So that's why you have more than one input data point, even though you have just one image. Okay, thank you. We can cover the linear regression model if everyone is happy with that. So as you can see here, this is just like a practical example. I will share the link with you afterwards in the YSI group chat, so you can all just like go through the examples yourself and even modify with the code, play around with this, right? So first thing here is I'm generating data like a simple linear like a simple function, right? So this is just a simple function, and what I did not mention, and that's another important thing I forgot, you separate your data into training and testing data. So, for example, the blue points here are my training data, and the black points are the testing data. And you train your model only on the blue points, and then look if it's like the accuracy is still like roughly the same on the black points. And this is one way you could measure overfitting. So if your model predicts the blue points very well, but the red points, the black ones, not that good, that's a sign your model overfit. So then you can like decrease it in size or do more dropout. I build a model here. So this is PyTorch. If you don't know how this works, it has a great documentation you can look up online, and they have like a weight. That's a random tensor and a bias. So essentially, this is just the function I showed you earlier without the activation function. And then I built this model, and it started off with a tensor of like 0.3 as a weight and a bias of 0.128. So the original predictions with this are not very accurate. As you can see here, the red points are far away from the black ones. When I trained it, I defined a loss function and an optimizer. So the optimizer is essentially just your gradient descent method thing that handles that. So here I used stochastic gradient descent, but there are also multiple other ones like Adam, for example, is another common one. Yeah, here's the whole process I mentioned. So it's very nicely documented, as you can see with the comments. So if you want to look it up yourself afterwards, it should be very easy to read, even if you can't, like, if you're not familiar with PyTorch or Python. So first we perform a forward pass to get the prediction of a model on the data, then calculate the loss with the loss function we defined earlier, zero the gradient, so they don't accumulate. Normally they like accumulate over time, and that's just errors your calculation. So that's where you reset that. Then perform backpropagation to know which parameters caused the error, and you gradient descent with our optimizer, in this case stochastic gradient descent, to modify the parameters so they model it better. Here, this is the output of the train data. As you can see, the loss is decreasing from 0.48 to 0.005, and the trading loss as well. So here is the nice loss function. As you can see, it goes down, and now the points are very close to the black ones. This is how it will work. I will share this this notebook in the chat so you can modify the code and look at things up yourself. Here. Yeah, of course, you can ask questions about ML neuroscience. I'm not that familiar with neuroscience. I'm more focused on the machine learning things, but if it's like similar, can answer that as well. How good a machine learning pattern recognition? Yes, it depends on your model, of course, but generally, it's the more data you have, the better it is, because it tends to be like that. If you have less data, you like miss out some examples, some data points that you can't learn that much, and it's easier to overfit. So normally, it's better to have more data than less. But we could train a model on less data. Any more question? Okay. If you have any more questions, feel free to ask them. Right. This is the Q&A part already. String data. How is it validated? Is it the same validation as the training data? Just you don't perform the backpropagation and gradient descent method with it. So it is not used to update the model's parameters, but you still like predict the output and then calculate the loss. So the loss score, if it varies too much, you know your model overfit or underfit. It's another problem if it's underfitted. It's too generalized, and then yeah, that's also not good. And another thing is sometimes you also have a validation set. So not only training and testing, but also a validation set, which you use afterwards to see if like that's another thing of validation, but it's not needed most of the times. Like a testing set does everything. Okay. If you have more questions, feel free to ask them. Right, this is the part like that's planned for that. So we have still lots of time.
Right. If there are no more questions, we can wrap up the session. If you guys have questions afterwards, I can forward them to the speaker after the session and he can answer them.
Yes.
Oh, there is questions. You can go ahead.
Yeah, okay. When you say calculating weight data, it's the same as scanning of a pixel. What do you mean calculating the data? So first, you have your pixels, right? You just get your pixel values, and then you perform your mathematical operations with your trained parameters to get your output, and then that output that is compared to the expected output to get your loss. So if I said calculate the data, I probably meant calculated the loss. The loss is the error between the prediction and the actual output. So the best way to start learning would be with a normal linear regression model. If you, the first thing you should do is learn Python. Okay, Python is the programming language you use for every machine learning task. Then you specify with a library, either TensorFlow or PyTorch. I personally prefer PyTorch, but TensorFlow is also a great library to use it for. And then I would start with the PyTorch documentation. Like if you just Google PyTorch documentation, there are tons of examples you can just follow, and they explain like the fundamentals of how to use this library very well. That's very great. It's a good starting point. But yeah, start with a normal linear regression model, and then just go further and further. You can also just go through all the notebooks I shared. I will share every single one of them, but if you go through all of them, you should have a very good foundation. Thanks for the